In this video, we will begin to explore radicals and their properties. The root of a number. A square root of a number is one of its two equal factors. For example, 5 is a square root of 25 because 5 is one of the two equal factors of 25. In a similar way, a cube root of a number is one of its three equal factors, as in 125 is equal to 5 cubed. Let a and b be real numbers, and let n be greater than or equal to 2, be a positive integer. If a is equal to b to the n, then b is an nth root of a. If n equals 2, the root is a square root. If n equals 3, the root is a cube root. The principal root of a number. Some numbers have more than one nth root. For example, both 5 and negative 5 are square roots of 25. The principal square root of 25, written as the square root of 25, is the positive root 5. The principal nth root of a number is defined as follows. Let a be a real number that has at least one nth root. The principal nth root of a is the nth root that has the same sign as a. It is denoted by a radical symbol. The nth root of a. The positive integer n is the index of the radical, and the number a is the radicand. If n equals 2, omit the index and simply write root a rather than 2 root a. Note here that the plural of index is indices. Now let's take a look at evaluating expressions involving radicals. The first example we have is the square root of 36. This is equal to 6 because 6 squared is equal to 36. Then we have negative the square root of 36. This is equal to negative 6. Again, because 6 squared is 36. We then have the cubed root of 125 over 64. Here we have 5/4 because 5 to the third power is 125. And 4 to the third power is 64. Our next example is the fifth root of negative 32. This is equal to negative 2 because negative 2 to the fifth power is negative 32. Then we have the fourth root of negative 81. Note that this is not a real number. And it is not a real number because it has an even root and it is negative. So there is no real number that can be raised to the fourth power and produce negative 81. Here we make some generalizations about nth roots of real numbers. So if the real number a is greater than 0, and n is greater than 0 and is even, then the nth root of a, we simply take the nth root of a or negative the nth root of a. If a is greater than 0 or a is less than 0 and n is odd, then we can simply just take the nth root of a. If a is less than 0 and n is even, there are no real roots. For example, the square root of -4 is not a real number. When a is equal to 0 and n is even or odd, then the nth root of 0 is always going to be equal to 0. Some properties of radicals. Let a and b be real numbers, variables, or algebraic expressions, such that the indicated roots are real numbers, and let m and n be positive integers. So number 1, we have the nth root of a to the m. Note that this can be written as the nth root of a all raised to the m power. For example, if we take the cubed root of 8 squared, that is the same thing as taking the cubed root of 8 first and then squaring that. This helps when we deal with some larger quantities because we can make them significantly smaller first and then make them bigger instead of making them even bigger than they are before we can make them smaller. Property number 2, the nth root of a times the nth root of b is the nth root of ab. So as long as you're taking the same root, square root, cubed root, fourth root, etc., you can multiply underneath the radical. So the square root of 5 times the square root of 7, we can put that under one radical, the square root of 5 times 7, which is equal to the square root of 35. Number 3, the nth root of a divided by the nth root of b. This is the same thing as the nth root of a over b. And we use this statement of equality often in both directions. So sometimes we will split up that radical, and sometimes we actually want to take the two radicals and put them together as one. Note again, b cannot be equal to 0 here because it is in the denominator. So the fourth root of 27 over the fourth root of 9, we can combine that to make it the fourth root of 27 ninths. And then simplifying 27 ninths, this is equivalent to the fourth root of 3. If we have the m root of the nth root of a, we can simply multiply those indices, so we have the mnth root of a. So here we're taking the cubed root of the square root of 10. 3 times 2 is 6, so that is the same as the sixth root of 10. Number 5, the nth root of a to the nth power is equal to a. So notice an index of n and an exponent of n will cancel each other out. And we'll take a look at why this occurs later. For example, the square root of 3 squared is simply 3. Finally, for when n is even and we have the nth root of a to the n, we want to write this as the absolute value of a. So even if we're taking -12 squared, and that's what our radicand is, so we're taking the square root of -12 squared, we want to take that and make it the absolute value of 12, which is a positive 12. However, if n is odd, so we have the nth root of a to the n equals a, we can simply take that root as what it is. So the cubed root of negative 12 cubed is negative 12. When n is odd, we don't need to worry about taking an absolute value. Here we can use some of those properties of radicals. So using the properties of radicals, simplify each expression. So for part A, we have the square root of 8 times the square root of 2. Notice that this can simplify as the square root of 8 times 2, which is the square root of 16, which is 4. In B, we have the cubed root of 5 cubed. Remember, when our exponent and our index match, we are simply left with our radicand, so this is 5. A similar situation here. Our index is 3, our exponent is 3, so we are simply left with x. And then the 6th root of y to the 6th. Because this is even, we need to make sure that we use the absolute value of y. And that is because 6 is even. That wasn't an issue for us in C because our exponent was 3, which is odd.